All right. In this lecture, we are going to derive the energy balance for the batch reactor. Okay, so let's do this, and let's start from the general form of the energy balance. So first, let's write that down. So the general form of the energy balance is going to be this dE system. So how does the energy of the system change with time? We've said that that is going to be equal to the heat that's added or subtracted to the system, plus the work that's added or subtracted, and then plus the energy coming in and out of the system via flow. So we're going to have flow coming in and flow coming out, and this is again the general energy balance out. Now in a batch reactor, we know we have no inflows or outflows, so we're going to take these terms and cancel them immediately out. So what we're saying there is that the flow terms go to 0. In this expression, this E-sys term, this is going to be the total energy of all components in the system. And it's going to be equal to a sum then of all these energies. Each of the components has an internal energy, a kinetic energy, and a potential energy piece. So this we're going to write here as a sum. Number of components, or I guess each component, so component I times EI, this is going to be equal to the sum of all of the individual internal energies plus the kinetic energies, we'll just say KE plus the potential energies. We're going to simplify this to get rid of those kinetic and potential energy terms. Talking about a batch reactor, the kinetic energy isn't going to have much of a contribution there. When we're talking about a system, the kinetic energy would be the system is itself moving. Typically a batch reactor isn't going to be moving, and even if it was, that kinetic energy would be a lot smaller than the internal energy. We can make the same exact argument for the potential energy term. So really the internal energy is going to be the energy stored within the molecule. This involves, for example, the energy stored within the bonds, and that's going to be a lot stronger than kinetic energy and potential energy, where here kinetic energy and potential energy are, just as we would think about them in physics, dropping a ball to the earth, for example. That's a lot smaller of an energy than the energy stored within bonds. So we're going to simplify this. We're going to say that the system energy is really going to be the internal energy, since delta U is going to be much greater than, so the change in internal energy over the course of a reaction is going to be much greater than the changes in kinetic and potential energy. Okay, so let's see here. I want to make sure that I'm capturing. Okay, yep. All right, so now we have this internal energy. We know from thermodynamics that internal energy is related to enthalpy. So internal energy is equal to enthalpy minus the pressure volume term. Since we ultimately seek a delta E-sys, so the change in energy over the course of time, which is due to a reaction. So we're looking at a delta E or a delta U. We can neglect the pressure volume term, since it's also going to be a lot smaller for the system than the change in internal energy. So we'll say delta PV is also going to be much smaller than delta U. That is not drawn very well. Let me rewrite that. Delta U in this chemical reactor what that allows us to do is to approximate internal energy and enthalpy being the same thing. So here we're going to say, so we're assuming delta U is approximately equal to delta H. That's a argument that is made often when looking at chemical reactions. This then says that the energy of the system is going to be approximately equal to NiHi, and so that means that this dE cis dt term is going to be d dt sum NiHi. Okay, so now we're getting somewhere. Next thing we want to do is apply the product rule. So basically we're going to differentiate each term in this expression that we just wrote. So we do that here. So dE cis is going to be equal to the, what do we have? The first times the derivative of the second plus the second times the derivative of the first. So this gives us some Ni dHi dt plus some Hi dNi dt. Okay, so to do this, let's start to quantify what these terms are. So what is Hi? So this Hi term, this is the enthalpy of the species. Maybe the enthalpy of formation, which is typically an enthalpy that we use when we write delta H's for chemical reactions. So we know that we can write that as being equal to a reference enthalpy plus a change in enthalpy due to temperature. If we do that, now we can differentiate this expression with respect to time. So we would say d dt of Hi at the reference temperature plus the integral from the reference temperature to T CPI dt. Here the reference temp, or the enthalpy at the reference temperature there, that's just some value. That's constant. So then we have the Hi dt. That is going to be equal then to, or I'm sorry, where am I here? So we have then our dHi dt. If we take that then and differentiate this term, so this term here is constant. So the derivative of that term is 0. So we'll say, so dHi at T ref dt equals 0. That means we only have to worry then about this second term. So we want to take, so our dHi dt term is going to be equal to d dt of that. Okay, so if we say that CPI is constant with time, except for changes made due to temperature, then what we can do there is to say that this expression here is equal to CPI dt dt. So what we're saying there is the temperature is going to change with time. So that means basically that this upper limit is going to change with time, which means that the enthalpy is going to change with time. But other than changes with respect to temperature, this CP term doesn't change, which is a reasonable assumption. Okay, so if we do that, then we can write our expression. We can write out our expression here. This is going to be basically putting together our dE sys term, which we said is equal to this heat plus work term. This is going to be equal to sum Ni CPI dt dt plus sum Hi dNi dt. So now we're getting somewhere. If we want to focus now on this term, and what we're going to do is recall that that is the mole balance of the batch reactor. And we know that that equals Ri times V. So dNi dt for batch reactor is going to be equal to the rate, the net rate of species I times the system volume. So then in that case, we can simplify even further. Our energy balance, this is going to be sum I CPI dt dt plus some enthalpy I RIV. The next thing we can do is say, okay, well here we have all of these individualized rate terms, and they're going to be multiplied by each of these individual enthalpy terms. So we basically have the rate of each species times its associated enthalpy of formation. We can use that. So we're going to use the law of relative rates here, indicating that I can relate the rate of any species to the rate of any other species. So here I'm going to relate to species A, which implicitly is the limiting reactant. What that allows me to do is basically say that the rate of any species is some multiplier times the rate of species A. That multiplier is going to be the stoichiometric coefficient of that species divided by the stoichiometric coefficient of species A, where stoichiometric coefficients will be negative for reactants and positive for products. And doing that, what we basically recovered then is going to be this expression. Where we have, hold on one second, where I find myself in my notes. This is going to be the heat of reaction. I don't know if I'm getting ahead of myself here. I am getting ahead of myself. Yes, let me write down all of the steps here. So then I would have this is going to be sum of the Hi nu I over nu A times negative RA B. Then what we have here is that we can take this piece of the expression. This is going to be the heat of reaction. If we then do this, then I should say this is heat of reaction per mole of A, where A is limiting reactant. If I do this, then the energy balance becomes Q plus W is going to be equal to okay, I guess I should leave that there a little bit longer. So we're going to have our heat plus our work on the left-hand side. On the right-hand side, we're going to have the molar amounts of each of our species times the heat capacities times the change in temperature with respect to time, and then we're going to have this heat of reaction times the rate of reaction times the system volume. Okay, I guess I was supposed to put that down here. So that's this piece right here. Let's see if I can grab the whole thing. So this goes here. And I can erase this to give myself some more room. Okay, so now we're going to solve for dt. We can do that algebraically. So that's going to give us Q dot plus Ws plus the heat of reaction times the rate of A times the system volume divided by our heat capacity terms. So now we have an expression here. Here, this term here is going to be our heat generated. Which we're going to denote QGB, so heat generated in the batch reactor. Q is the heat removed. Probably it's removed. Maybe it's being added. We're going to call that QRB, heat removed in the batch reactor. And this is going to be equal to this UA delta T term. TA is the cooling fluid temperature, which we're going to assume is constant. So what this tells you is that if this term is going to be positive, if that cooling fluid temperature is greater than the reactor temperature or the system volume temperature, and it's going to be negative if it is lower, if this cooling fluid temperature is lower than the system volume temperature. Okay, so that when we think about this here in this positive term, the way we've written this is going to reflect that. So if this quantity, if Q is positive, then it's going to increase temperature with respect to time. If Q is negative, it's going to decrease temperature with respect to time. So we've done our proper accounting there. All right, so now let's write this in terms of conversion. So to do that, we want to sub out these values of N, so that's molar amount, and if we want to write instead of in terms of conversion, then we need to write expressions for N in terms of conversion. To do that, we can use the definition of conversion. We're going to say our limiting reactant times theta, so theta is this ratio of initial molar amounts. Oops. And then we're going to say minus our stoichiometric coefficients, again, which are negative for reactants and positive for products, times X. If we do that and sub in, we get this expression, and we should say we often neglect the work term because unless you have a pretty viscous fluid, it tends to be pretty minor compared to the heat generated and heat removed to the heat generated to the reaction, the heat removed to the heat exchanger. Okay, so here's our expression for our batch reactor. We can make further adjustments. So we have this term here on the bottom. This term is going to be equal, or this term, what this term reflects is the change in heat capacity per mole of A that reacts. We're going to denote this as delta Cp. In that case, then, we say our energy balance is going to be our Q term times our heat generated term times this delta CP term, and this is going to be our final version that we can use. So let's do some examples to kind of quantify some of the pieces in here. One is calculating this delta CP. So we're given an example, the reaction A plus B goes to C is carried out in a batch reactor. We're given heat capacities for A, B, and C. We want to determine this delta CP term, for example, here. So delta CP is going to be equal to, I am not doing a very good job at drawing the Greek letter nu today. It's going to be equal to this expression. So basically what I'm going to do is take each species and take its stoichiometric coefficient, normalize it by the absolute value of the stoichiometric coefficient on A, which is positive 1, and multiply by its heat capacity. So I'm going to say, if I take all those, I actually get negative 1 is being nu A divided by the absolute value of nu A, that's negative 1 over 1 times CP A, plus negative 1 over 1 CPB, plus 1 over 1 CPC. That's going to give me CPC minus CPA minus CPB equals 46 minus 35 minus 18, all in, what is that, calories per mole Kelvin. Which is going to give me negative 7 calories per mole Kelvin. So that's how I calculate that term. Another symbol in here is this theta term. So let's recall how to calculate that. This says, for the same reaction, the inlet molar flow rates are 1 mole of A per minute, 2 moles of B per minute, and 0 moles of C per minute. Let's not do molar flow rates, let's say amounts. And so then let's get rid of these per minute terms. So we initially have 1 mole of A, 2 moles of B, 0 moles of C in our reactor. So let's determine our different theta i's, assuming A is the limiting reactant, which here it is because A and B are reactants 1-to-1 ratio, but we have 1 mole of A for 2 moles of B, henceforth A is the limiting reactant. That's going to be hence our basis. We're going to say NiO divided by NaO. So then theta A is going to be 1 over 1 equals 1, which it should be. Theta B is going to be 2 over 1 equals 2, and theta C is going to be 0 over 1 equals 0. All right. The next question says the reaction is carried out adiabatically. That means that this Q term goes away. So this Q term goes away, meaning that also this Q term goes away. There is no heat removal here. So we have two options if we want to write this adiabatically. The first, maybe the most straightforward, is just to say, okay, I'll just eliminate that term from my energy balance expression that I've already derived. And that is perfectly viable. It can be easier, however, to use an algebraic expression. So there's an algebraic expression I can use, and this is a general algebraic expression for all adiabatic reactors. This basically says that the heat generated is only due to the reaction, there is no heat removed. So the change in temperature is only due to the reaction, which is due to the heat of the reaction and the progress of reaction. So the heat of reaction here, progress of reaction here, and of course it's going to be, the temperature change is going to be tempered by the heat capacities of the fluids in the system. So this is a general formula. I can use this for any adiabatic reactor. It doesn't matter which reactor it is, and the reason for that is that there's no heat exchanger. So the only thing changing the temperature is the reaction itself. So I don't need a specific energy balance in that case, because the reason to have a specific energy balance is when your reactor is treating the system in a certain way based on certain assumptions for that reactor. That's not the case, at least in terms of the energy balance here. So this can actually be a little bit easier. You don't have to solve a differential equation to do this. But either one of these ways is viable when you have an adiabatic system.